Okay, good afternoon, everyone. So let's start. And also to those of you who are on the Zoom, um, so this is for those of you who are on the Zoom. If you have any question, just speak up loudly. Don't use the chat because I'm not able to monitor that. Okay, so welcome to 202A. And I guess the first 40 minutes or so is just a bunch of logistic items that hopefully will help you make up your mind. As you know, the class, like with all the courses here, is oversubscribed. So just want to go over that. So okay. So firstly, a bit about myself. Um, uh, Faculty in both ECE and CS department. ECE is my home department. Um, I largely work on the topics related to this course, namely, I work on computing systems which interact with the physical world, with humans, and kind of everything around them. My lab, 1762 Bolter Hall. So as you enter this building from kind of the southwest corner, from that alleyway, if you enter on the first floor, right opposite the elevator, it says Networked and Embedded Systems Lab. So that's where my lab is. Um, I am originally from India, did my grad work at Berkeley. I used to be VLSI signal processing type person, but then over the course of my career, I've kind of moved up the computing system stack. And I guess within my own discipline, um, there has been considerable shift, mostly like every other discipline, namely the emergence of AI and machine learning methods has really changed how we process sensor data, how we do signal processing, how we do control. So a lot of what electrical engineering and computer science used to be about have gone through a lot of shifts. So my research group, which is 7 PhD students and a postdoc and some undergrads and master students who hang around, it's kind of largely we work in those. We publish in conferences in AI. We published conferences in computing systems and networks. Okay, I also have 20% appointment at Amazon, their AI labs, just to get some industrial perspective on what I do. My office is on the floor above, again, kind of in that corner of the building. So office hours, currently I plan to hold them one in person, 6 to 7 p.m. So basically right after the class on Tuesdays. Yeah, in my lab, I think it's a more convenient place. It's bigger than my office. And then on Friday by Zoom, 4 to 5 p.m. And then you can always kind of reach out and set up time for appointments. I guess Thursday, same time, 6 p.m. is also a good one. But I also realize after 2 hours of class, you probably want to have dinner and all. So I didn't want to keep both office hours that way. You've already seen a bunch of emails from me. We are extensively using Piazza. Um, and so if you need to contact me for anything, the preferred modality is to use the direct messaging feature within Piazza, okay? I have configured Piazza so you can send direct messages to me, but you will not be anonymous. In some prior incidences, that anonymous feature was being misused, so I have disabled. So if you want to communicate anonymously, use some other mechanism. And of course, among yourself, you can resort to Discord or whatever, but within Piazza, I will get to know your identity. You can always post it so that your peers don't, but it will always be visible. So just wanted to make that clear. If you do decide to email me, quite possibly it may get lost. I get a lot of emails, but try to put 202A or 213A as in the title. Okay, so that's about me. I've already described this, so as of this morning, the class had a waiting list of 105 or so, and I've already handed around, I think, 10 or 11 PTEs. So here is the deal. There's, as you'll soon see, there is a reason why there is a cap on this course. So, and that's aiming for 30 students. So since I've already handed out, I think it's 10 that I've handed out, might be 11. Yeah, so that basically means there are roughly 20 spots remaining. One or two people who I handed out PTs are kind of waiting for their visas in China to be given out. So there'll be some clarity in a few days there. So priority order MN students, because they are required to take this course. Yeah, so yeah, they get the priority. And after that, basically, if you're a PhD student or MS leading to PhD, which is another way students in ECE are admitted and are working, and within that subgroup, if you're working in topics related to this, so kind of depends on who your advisor is, you get priority, and after that, everyone else. And then students who are from outside ECE and CS, realistically, no chance that you will get in. Um, um, there might be one or two undergrads who are our department scholars. So again, I kind of, there are smarter students, so I kind of try to accommodate them. Okay, so to do well in this course, you should basically have done a computer engineering type degree in the undergrad. I mean, that's a rough way of defining things, which basically means should be comfortable with computer systems, kind of things around it. So some architecture, some operating systems. This is not a hardware course, so it's not about getting into circuits and all. But you should certainly, like, how does a CPU work? Be comfortable with low-level programming, should know a systems type programming language, so like C, C++, Java, something like that, because that's how you program embedded hardware. And also, as I alluded to, sort of machine learning models and all are used quite a bit. So again, assuming that through your undergrad, you have done some course, ideally on machine learning, where you have learned how to take data, train models, ideally neural network type models, because again, it's not simply machine learning models, but it's pretty much deep neural networks which are being used out here. So prior exposure to that. Having said that, it's not like rocket science. So yeah, you can pick it up. There's plenty of material on the web, but I will not teach that. That's not the intent of this course. Partly also because most students have done such a course. So if you haven't, you are welcome to attend, but just be prepared for some self-learning. If you don't, and I think one way I will sort of give you some senses, there's an assignment. I didn't do it in preceding years, but I'm going to hand out an assignment this just in a few days. And if you struggle with it, then perhaps the course is not for you, at least at the present moment. Okay. So what are the objectives in this course? From my perspective, there are 4 learning objectives. So firstly, I don't believe in teaching you skills relating to technology of the moment, because they change. So I think maybe it's a bit old-fashioned. I think learning about the foundational stuff is far more important, because they kind of carry over, and learning how to solve problems. Okay, problems which require you to extrapolate. So a lot of the topics are really kind of fundamentals of what I would loosely classify as embedded systems that are connected and are AI based. So those qualifiers, because that's what modern embedded systems are. Uh, I also realized that you have to get jobs and all, so getting some hands-on experience with relevant technologies and all, but just bear in mind, they change rapidly. Okay, I mean, what's true today, just in a small number of years will change. So to complement that, it's also exposure to the research frontier, and you'll see briefly, shortly, how we kind of do that. And then finally, really, my style of teaching is not to test you on what was there in the lecture. In fact, lectures are kind of just pointers to things out there. It's really you learning how to kind of solve problems based on the knowledge you have, which nowadays often means that judiciously using material which is out there. From my perspective, using AI tools and all is totally fine. So because again, modern engineers and scientists work that way. So those are, by the way, again, feel free to interrupt yeah, as I kind of go along out here. So the structure of the course, basically kind of obviously lectures. And the initial part of the course would be more lecture dominated. But the lectures serve to kind of for different topics, provide the background, what are the challenges and some of the techniques which have become established. And then complementing it, and this would become more use of our class time in the latter part of the quarter, which is student-led paper presentations, reviews, and discussion around them. Okay, so I'll describe a little bit more in detail, but kind of the idea is it's a rapidly moving field. Literally every month there is some conference and there are some new techniques and ideas emerging. So I want you to also get some exposure to that. And in fact, one of the reasons the capacity constraint really comes is from this, because I can't accommodate this style of teaching with a large class because it takes real time. I mean, then I wouldn't be lecturing at all, and even then I wouldn't be able to accommodate. So the cap partly is a result of that. There is also a course project, which is a major part of the course. Um, um, Sort of, I think ideally do it on a team of 2 or 3, but some students do it solo also, and can take various forms, solve some novel, interesting problem, measure and analysis type stuff, very common in this space because there are new technologies, new platforms, those kind of things. Do some cool end-to-end application, but again, it has to be cool. I mean, there, as in, it should be something where, like, my first reaction shouldn't be, I'm telling you there are 10 other things that have done. I went through that in recent years during pandemic, like half the class wanted to do some sort of a smart mask or a mask detection or something like that. And at some stage they get kind of very, very similar. I think in general, I think projects which simply collect data, train a model, high schoolers do it nowadays. So this is a grad course. So your stuff has to have more challenge to it. And or create some useful design tool, maybe explore the use of LLMs in order to design these kind of systems. There are lots of possible sort of projects, so project ideas, and we'll hand out some of those. Okay, so that's a third component. Final component is assignments. They would require analysis, architecture, coding, literature, some combination thereof. Currently, my plan is to release them at week 1, 3, 5, 7, and 9. Sometimes I get lazy or the class slips behind in terms of lectures, so I bundle them up. But at least that's the plan. It's mostly to make sure that you're keeping up with the course. And the way the late days work is that you can, if you take a late day, you lose 25%. So effectively, you have 4 late days, but with a linear decrease in your score. Accordingly, so let's plan things out. The questions thus far? Okay. So some other stuff about the course protocol. This is an in-person course. Okay, so you are expected to attend. Unfortunately, I think the past year or two, as a continuation of what was an online course during pandemic, I think the expectation set in that I would record and live cast, and I did do that. Unfortunately, there were many students who just stopped coming, and that kind of defeated the purpose of the course. So this year I've kind of decided that yes, I'm recording, and of course this lecture is being simulcast because of practical reasons. But after this lecture, that won't be the case. I will still record, but I will give access. I'll let you into the Zoom room, and I'll give you access to recording only against some valid reason. And I think basically there are 3 types of reasons that sort of currently I encounter. Medical issues, including, of course, your near and dear ones, but I need some sort of a validation. You can't spring it up weeks later or something like that. Okay, so this one. Second one is some of you are research students and you may have some conference talk to give. So that kind of conflict, obviously, I'll accommodate. And also we have, actually this year we do, someone who's on one of the UCLA sports teams, so they travel, and so they have conflicts as a result. Again, I accommodate those. So those are the three things. Things arising because you are working on a second job isn't, because actually officially we're a full-time program, so you shouldn't be. So job-related stuff isn't, and also, unfortunately, our registration system lets you enroll for courses which are on the same time slot. Most universities don't allow it, but UCLA for some reason does. Again, that's not my problem. If you shouldn't be taking two courses in the same time slot. That's just a recipe for disaster. So those are not reasons for giving things. And then, of course, maybe once in a while there might be some reason. I'm kind of tolerant of it, but again, kind of the intent is I want you to come to the class and engage. Okay? So public access to the recorded videos would basically be significantly delayed, maybe even in end of the quarter. Just also wanted to just mention that your voice may incidentally be captured. So don't talk about stuff that you don't want the public to hear. Okay, so just stick to class-related material, because it's not, I can't go and edit things out. So. Okay, syllabus. Now, of course, some of this won't make sense because I've not talked about rest of the course, but since officially I'm required to put it out, so this is a structure I have currently in mind. I'm just going to walk through, of course. So I think of these things as modules, because kind of aligning these things to a class is very hard. So usually I have 10 to 12 modules in a course like this, some sort of coherent set of topics. Today's is partly this course logistics, but partly also kind of give you my take, certainly shaped by my research, on what is happening in this space of embedded systems, in particular, how things are evolving from classical embedded systems, like when kind of long back when think embedded system would be like a toaster or a microwave oven and all. Of course, we are long past those things. So historically, we have these phases from standalone, classical, simple embedded systems to things which were networked. So there were all these things like IoT and wireless sensor networks and all. Then emerged kind of more sophisticated interaction between computing and physical world under the name of cyber physical systems or human cyber physical systems. So we kind of lived through that. And nowadays, with the kind of incorporation of AI methods into this, you have terms like AIoT, AI, IoT, that, or AI-enabled cyber physical systems, or embodied AI, kind of referring to things like robotics and autonomous vehicles and kind of things, essentially AI, which is interacting with the physical world. Okay, module 2 is about hardware platforms. So accompanying that transition, there is also a lot of stuff happening. So again, good old embedded systems used to be microcontroller or some CPU, but nowadays we have all sorts of different processing elements and sort of trade-offs that have come with it. Module 3 is the software stack and the runtime environments that go with it. Again, like Arduino and all, I would put them into the classical thing, but then you have newer things emerging like tiny ML and all, which are supporting the machine learning side of things, and even distributed versions of these that are emerging. Fourth is a bit of a more classical topic, but it's very important, and which is when you are in a resource constrained setting, how do you schedule and manage resources? How do you deal with time constraints and similar memory and safety requirements and these kind of things? So we are basically kind of going to look at that. Module 5 is, since getting connected was a big shift in these systems. So the networking in these systems, firstly, a lot of it is wireless, but even when it is wired, it's kind of different than what is used for normal sort of computing needs. Oftentimes you have to meet latency requirements. We are very energy sensitive. These kind of things. Maybe you need to also not simply transmit, but also time synchronize and discover location and stuff like that. So the protocols and standards kind of have some additional stuff, and so we talk about that. Then module 6 is time, clocks, and synchronization. I guess one thing which distinguishes these kind of systems a lot is that they interact with the physical world, and therefore they have to keep up with the physical world. And also they coordinate multiple robots or multiple sensors. So having a notion of time so that you know whether you are meeting your deadlines and all, and coordinating, namely synchronization. Those are pretty crucial. So we are going to do a bit of a dive into that and what kind of technologies and all exist. We are kind of there things like GPS and all, obviously, but there are a whole slew of other technologies. Then we'll switch gears a little bit and get into how do we process the data. And kind of if you think of these systems, you have sensors capturing information from the physical world, then you kind of try to make sense of that sensory information. So think of like the thinking process, that's the processing part. And then finally you make some decision about some action to take, and that's a control part, right? So it's perception, cognition, action. You can think of it like that. There are other terms like this. So we'll start with looking at how do we make inferences from sensor data. And I guess we have gone through sort of methods which were physics based or first principles or logic or rules to then simple forms of machine learning to now increasingly, I mean, or most of the time, the best performing things are neural networks. So kind of we are already in that thing. And then further changes are happening. Okay, so there is this concept which have emerged now that instead of training a new model for every time I'm designing a system, can I have so-called foundation models, namely a model which we train on lots of data, and then when I face with a given deployment or a given task, and I rapidly tweak it, tune it for that. Okay, so a lot of action happening there, I guess. So we'll talk about that. So kind of both classical methods and deep sensing type stuff, deep learning type stuff, and then the shift from just sensing to control. Some of you may have heard of terms like reinforcement learning and all. In fact, the most recent Turing Award was given for reinforcement learning. So it's the computer science analog of control theory, okay, with deep neural networks. That's one way of thinking about. So we are going to talk about these kind of things. And then the other thing that's happening in this space is it's not just standalone devices talking with each other, but increasingly also kind of talking with services in the cloud. So a lot of IoT type services are supported out there, and there's a lot of emphasis out there in data centers, and a lot of emphasis on making latency back to data center, to the data center and back, sort of low and affordable. Okay, so this kind of an edge cloud, multiple tiers of distributed systems, how what is happening there. And finally, not sure whether I'll get to it, but kind of I certainly hope to cover it, at least give you some sense of what kind of issues and all arise when you have concerns of safety, reliability, trust, these kind of things that clearly is very important in these class of systems. So that's the lecture outline, the sequence in which we will go. I've kind of altered it a fair bit from last year. So if you are if you're looking at last year's material, it would be different, investing time on that. Any question? Okay, so another way of examining that those topics is kind of from a cross-cutting perspective also. Some themes run across them. Resource constraint, I mentioned quite a bit. You have limited memory because you have tiny stuff, limited energy, limited bandwidth, all sort of kind of stuff. There is this whole notion of latency, accuracy, energy trade-off. Normally in computing, we kind of, for the most part, kind of focus maybe a little bit indirectly on latency, but most of the time it is about like, you know, optimizing the throughput and optimizing the memory footprint and all. Here, latency, accuracy, these things you can trade off. Oftentimes, my computation can be slower and more accurate, or it could be faster and less accurate, and both will result in equally satisfying application experience. Okay, so those kind of trade-offs. And then oftentimes they can be traded against energy or some other resource like that, bandwidth, memory. Issues of being able to trust the result, okay, robustness, if you may, and security. Issues of scale and being networked, distributedness, life cycle of these systems. That's super important. You don't just design and deploy and forget. These systems need to be maintained and evolve over time. So there is a lot of technologies and all and ideas kind of relate to that. And then finally, these systems don't just operate in isolation. A lot of in many applications, they interact with humans in various relationships. Human may be providing observations, human may be the actor, human may be just a third party nearby. So there are lots of issues like that that come. So these are going to be some strands, not that will cut across some of those topics. Okay, so in light of that, how would the various things be contribute to your grade? So you'll have to make one paper presentation. So I'll stick to 30 student cap. Probably there might be some attrition, in which case I'll have some more lecture time, and that's fine, but I can't risk it in the other direction because that eats into some planning for 30 students, 15-minute presentations, which includes 3 minutes of Q&A. So it's like a 12-minute presentation and 3-minute Q&A. 12-minute talks in conferences nowadays is pretty routine. So part of it is also getting the ability to convey things crisply and without kind of meandering. So like you don't have to repeat every time, oh, sensors are important or control is important and all. I think come to the punch line, kind of focus on what the new content is. So so think of it like this is also an opportunity to kind of practice your communication skills. Okay, so one paper presentation, that's 10% of grade. 5 paper reviews, so we'll have up to 30 people presenting papers. I will assign to everyone in the class 5 of those papers that you will provide kind of like a page review of each one of them. It's more like it's not a summary, but it's an analysis, it's a critique. Okay, now I also fully realize that most of you will probably use ChatGPT or Claude or something like that to write it. It's I can't with that. But you are responsible for what you write, and just like if I suspect you are writing like that, I'll probably also use an LLM to grade it also, and so it will work. It can work both ways. Okay, so but so anyway, that's what the paper reviews. So each one of them is basically 1.5% each paper. N paper discussion, N is 30. Okay, so kind of the idea is that 3-minute time duration for the discussion. So the way I would structure it, that the day of a paper or set of papers, the speaker submits the slides, and everyone in the class have to submit one slide where they have to put down their perspective on the strengths, weaknesses, some analysis of the paper. Enough so that you have the talking points, and then I will select from that, and then you have to lead the 3-minute discussion. Okay, kind of present your perspective, and then everyone chimes in. So this way, everyone gets to speak. It also solves my problem of keeping track of who contributed or who didn't contribute, because it is part of the grade. So the discussion. Course project. So course project, as you can see, is almost half the course, because it is also the most time-consuming part of the course also. So one thing every year I see is that some students take it way too easily in week 6, 7, and they're still struggling to even define the project. Okay, so last year I started this, and okay, so you have to have a proposal discussion with me, or if the project topic has a mentor, usually one of my PhD students, then with them, but you need to have 2 meetings with us in the first 3 weeks, excluding this week 0. Okay, so week 1, 2, 3. Okay, and then you have to submit a proposal write-up, which takes the form of setting up a GitHub project, GitHub repo, a GitHub project page, and putting in some of the initial information we asked. I'll provide some more details. There's a midterm presentation. It is scheduled for November 13, which happens to be a day when I am actually happen to be on travel. So it's one of the 2 days in the quarter which are the Zoom days. There's one more. So we'll do that all on Zoom, which is probably also more efficient because it saves time for each student to come up here and all. So we are going to conduct it all on Zoom, midterm presentations, basically what problem you're doing, what all approach you have identified, any preliminary sort of results you have had. So that's week 7. So it's kind of, you would have had 2 to 3 weeks after your proposal was finalized and submitted, proposal submission was done. So you have 2 to 3 weeks. And then finally, during the exam week, final presentation demo and finalization of, I've listed as report or website because the website of your project is your report. Okay, so there's no separate like term paper style PDF that I expect. It's your website, which is a report. And again, it has to be on the GitHub project page there. And then finally, the assignment, which I already talked about, that's 22.5% points. Okay. Questions on this? Nope. Okay, so grading algorithm, I just wanted to describe that a little bit. So some of the things in the course are kind of subjective in nature. Okay, so I can't give you like fine-grained numerical score. So what I tend to do is I kind of map it into where in the stack of sort of standard grading, letter grading they fall. So A is like correct or high quality, B is some flaws are acceptable, C is significant flaws, below average quality is a grad course. So C means you're already kind of below median. And D is kind of unacceptable, and F did not make a serious attempt. And then what I do is I kind of go back to the following thing, that A's are some form of 90s, B's are some form of 80s, C are in 70s, and all kind of, I go back and forth between this numerical and letter grade thing. And if on anything, let's say some assignment, I think almost every other element of the course, the grades tend to be fine, but assignment sometimes I misjudge. The numerical scores tend to be too low, in which case I kind of adjust so that the median becomes again 80. So I kind of rescale them. Essentially, the median slash mean tends to be kind of on the scale of 4, like 3.5, 3.6, something in that neighborhood, 3.65, depending upon the year. Most of the time it is like B plus, A minus, or A, kind of that range. Some Bs are occasionally, you have to really kind of sort of not do anything or fight with me or whatever, something like that, to earn a lower grade. But most students naturally do fine. But you should do your fair bit. Okay, hopefully kind of you learned something. So that's the grading algorithm. You can kind of read it at your leisure, more depth. Project is your opportunity to dive into some area which in a deeper manner. So I think what works well is if the project is aiming for something interesting, potentially hard, but focused. Okay, so trying to complicate the project by slapping on lots of different things never works. Okay, so keep the things focused. So we will provide, usually kind of what happens is at this time I ask my students to kind of suggest some project topics. I have, and of course, we are not limited to it. Many students come up with their own project ideas. Sometimes they are inspired by research or prior projects, or maybe even jobs that they may have done. Main thing is you need my approval. Some of the considerations, the project is not something where like zillion other people have done it. Certainly something where you can just download software and submit it as a project. I mean, that's not terribly satisfying to anyone, shouldn't be to you either. It's not even a learning experience at that point. Those kind of considerations. I don't want multiple teams to be doing, too many teams to be doing the same project or similar project. So those kind of things lead to sort of whosoever grabs a project idea first. So very important to formulate a team soon. Usually people pick up their own trends, but I also realize that for many of you, this is the first quarter. So use Piazza to reach out if you're looking for partners. Describe your background a little bit and say, kind of just looking for someone and talk. I think doing solo, you should do only if you're super confident in your skill set and background, and maybe your availability time-wise is pretty hard. I realize some people do jobs and all, so that's. So another thing I just wanted to mention is that UCLA, I'm not sure if those of you are new are aware of this yet, but UCLA allows you to drop a course until the last day of the 10th week of classes. Okay, so that means you can drop this course until December 5. Every year, what happens is around late November, early December, someone will come, but my partner has dropped out. What do I do? So, few things. Firstly, not my problem. This is kind of the first thing I would start out by saying. You should not pair up with someone who you don't trust that they will drop you. Okay. So that the other thing is, all of you are adults. You might face similar problems if you're working in your own startup or any other company and all, and you just have to figure out, go for it. The maximum thing I can do at that point is to give you more time, maybe just work with you to modify the project into something a piece. This is why it's also important that as you approach these things as a team project, kind of organize the project in some manner so that you can cope with that kind of a thing. But foremost, kind of just get early signs. I mean, if during the first 3-4 weeks when you are doing the project proposal, if some members of the team are not carrying their weight, they are not good team members. Okay, so run away is the only thing I can say. You don't want freeloaders, and that usually becomes apparent very early on. Recipe for disaster later on. I mean, I can't give you a free grade, and obviously my choices are limited. I can give you extension of time, but those are kind of the only things. So, and again, I grade these things based not so much on the result, but the result relative to the quality of the project. You may have a fascinating result, but if it simply meant you downloaded code and just sort of ran it, you're not going to get much credit. On the other hand, if you attempt something interesting and hard and fail, that's fine. I've given A pluses on that, okay, because negative results have value too. So aim for something, I mean, wherever your comfort zone is, but kind of that's how it works. And of course, the team size has to be justified by the project proposal. Some projects are kind of more suited for 1 or 2 people, and some may be 3, or on rare occasions. In fact, the best project last year was a team of 5, and they took something very ambitious and kind of pulled it off, and that was justified. They were all kind of doing different pieces. So kind of you can make the case for a bigger team, but of course, bigger team comes with more interpersonal challenges. So you make sure that you're comfortable going down that path. Question on the project. So actually, they are already on Piazza. So if you not if you're not on, like, you have to be registered on Piazza using the access code, because those are, so for the last 3 years, all the projects are listed there. Which link is? Is there any specific project not working on? None of them are working. Oh, no, that one is about project ideas for this year, right? I mean, the projects from last year, previous years are all there. Okay. Yeah. Okay. Yeah.
Wondering, for the enrollment for the course, there were like 4 categories. People in the 3rd category just off the wait list. When do you expect them to finalize?
Look, realistically, since I'm going to hand out our homework, I don't expect you to do the homework if you have 0 chance of getting in. So I would say by early next week, I would just give you the clarity on where things are. Okay. And yeah, so that's what I could say. Usually, um, uh, after the first lecture, today's lecture, a lot of people will drop out naturally because whatever, they don't like my style or they don't like the material, any number of reasons. So things shrink quite rapidly. Yeah. Okay. Any other question? Okay. I mean, there's always an option that if you want to risk it, hang around a little bit longer, follow along that homework and all, and if a slot opens up later in week 2 or something, then you can get it. But again, that's going to be your choice. Yeah. I think right now 2 people are sitting on PTEs because of visa issues. Even among those who have taken the PTEs, I'm pretty confident some will drop out after this. So, yeah. Okay, as you think about a project, there's something which those of us who do proposal writing or new projects and all for a living, like professors and such people. There is something called Hallmark Catechism, which is kind of a go-to thing. So there's a former director of a major funding agency called DARPA, Defense Advanced Research Project Agency, which brought you internet and a whole bunch of other things. He kind of always would frame sort of a new research project or a research program proposal in kind of a set of these things. What are you trying to do? Articulate your objectives with no jargon. A lot of times when people are proposing something, they try to impress others with throwing a lot of jargon and all. Okay, and kind of no, if you have to be able to explain simply in simple terms. How is it done today, and what are the effects of, what are the limits of the way it is done currently? What is new in your approach? Why do you think it will be successful? Who cares if you're successful? What difference it will make? Now, some of these things may not quite apply to a course project. What are the risks? So in course context, the risk is if your project depends upon acquisition of some hardware or some software which you don't know currently works and all, stay away from those things because you have literally a few weeks to pull this thing off. So whatever ingredients are needed for your project should already be in place or should be easily acquirable. How much will it cost? It matters in the sense that while I do support the projects with things, but I mean, I either have to do it out of pocket or if I can double dip into my research funding, but there are limits. Okay, so can't, unless you have independent access to something costly that you might need, we can't. Okay. My lab is pretty well equipped, so a lot of stuff that you expect you might want to use there. UCLA also has things like Maker Lab and stuff, so there are a lot of other resources. There's Keysight IoT Lab, which has a lot of instruments, which I'll provide you guys access to. So like if you want to solder or use an oscilloscope or these kind of things or do some measurement, depending on the project, you can always kind of do it. How long will it take? Of course, you have to finish it this quarter. And always think about what is it that you are setting out as your objective. Okay, something like what are the metrics that you are putting there? Could be functional metrics or performance metrics or something, but there has to be things so that you can cross check against it and are things going well or not. Okay, and be able to do it continually. Otherwise, at the end, you will have surprise. Okay. Project timeline, I've kind of listed out here. So week 0 through 2, kind of discuss project ideas with me, or even sort of just by way of, oftentimes what happens is students come, they describe their background, prior experiences, and then some project idea emerges during that conversation also. I mean, fortunately, this topic is rich with possible project ideas. Week 2 to 4, a second mandatory meeting, okay, and I want you to document both of these meetings by essentially one person in the team sending a direct message on Piazza saying we met, this is what we discussed, these are the takeaway or action items or whatever. Okay, so that becomes part of your record. So that's your responsibility to do it. If I don't see that, then for me the meeting didn't happen. Week 5 is the initial project proposal, kind of a formal one, which is basically project repo plus website, and then you'll fill out a Google form to give me that information. Week 7 is the midterm checkpoint on Thursday, 11/13. As I mentioned, that's a Zoom day. So we're just going to do it online. And this is where your website should be updated with additional thing like what data, tools, methods, preliminary results, those kind of things. And then finals week, 15-minute max presentation, including any demo. Most people tend to do it on Zoom, but you can also do it in person. There's a 3-hour final exam slot, which basically means that I have 12 project presentation slots during that, but given changeover, things slipping and all, let's say 10. Usually for a class of this size, I expect there will be maybe 15 to 20 projects, which means that some other projects will have to be outside the final exam slot. So I sort of give a whole bunch of slots and you sign up for it. And yeah, so that's what sort of the project schedule looks like. You can, again, look at last year's projects, the reports and all to kind of get the sense of what kind of thing people do. Paper presentations. So this I used to do, I stopped doing, particularly because it became hard to do during the pandemic, and now I'm kind of reviving it. So papers from recent literature relating to the course topics, essentially giving a sense of what's the most cutting edge approach or problem. 12-minute presentation plus 3-minute Q&A. This is an estimate because I've calculated it based upon 30 students, but if there is attrition, maybe there'll be some slack. Presenting student submits a slide deck for the talk and makes the presentation. All other students will have to submit one slide with basically strength, weaknesses, and kind of opportunities bullets. And then I'll pick one out of the submissions, and you have to lead the discussion. During the course, you will also have to do in-depth reviews of 5 of the papers, of course, excluding the one which you presented. So 5 papers, which I will assign to you. So it's not like you pick 5, I just want coverage of the various papers. Okay, questions? Okay, there'll be a schedule for this, which I've kind of prepared, but most of these presentations are towards the end of the quarter. I think the first one starts towards I think around October 20, so kind of roughly a month from now. Okay, so there's nothing in the initial weeks. Course on the web, you already see, so I'm not using Bruin Learn. If you go there, you'll see link to the things, everything on Piazza. Submissions is through Gradescope. I've not set up Gradescope yet, but if you haven't used it, it's a system where you upload PDFs, source code, stuff like that. It has support for auto graders, things like that. So, but you'll need to log in using your UCLA Bruin Online ID. And then we use GitHub for projects. When you do GitHub, make sure that you make it accessible to me, because oftentimes what happens is people submit stuff, particularly at the time of the final thing. They submit, they go away, and then when I start grading, I discover parts of it is non-readable, non-public, and then I'm left with very limited choice, but to give you an incomplete. The other thing to remember is that one reason I use GitHub is GitHub also tells me when you actually did something. So you can't backfill your project proposal later, right? I mean, GitHub has all your updates, so it gives me a timestamp. So they have some students who have attempted to kind of backfill their prior work to make it look better after the fact. Don't attempt. I mean, everything is timestamped. What do you need for the course? So there are no required textbooks, but there are some free books which are good. I think traditional embedded system books, they're pretty boring. I think there's a lot of material out there, so I wouldn't recommend any of them really. If you don't have a good operating system, if you have never done operating system and all, maybe you might want to look at some book around like FreeRTOS or some such embedded OS just to get the concepts and all. But I think what are useful are a couple of books that have come out on machine learning in context of embedded systems, and there are kind of 2. One is by this guy Pete Warden from Google called TinyML. So TinyML basically refers to machine learning for tiny stuff for resource constrained devices. And then there is machine learning systems by this faculty, Professor Reddy from Harvard. And he teaches a course around it also. So again, it's all available. And both these things have a lot of material, tutorials, ready to run things and all. Okay, so that's good. What else do you need for the course? So of course, you are going to be working on with real stuff. So I'm kind of assuming that all of you have laptops to develop stuff in. Should be reasonably recent vintage so that you can install modern software, Arduinos, and use it as a gateway or a server for your projects and things like that, or even assignments. Smartphone of some form, both Android and iOS at this point have a lot of interesting apps and all. Unfortunately, some of them tend to be paid, like particularly for collecting sensor data and streaming it and all, but they are useful. But as long as you have a phone, you can, there's plenty of stuff around. And then finally, some sort of an embedded device. And this you would need very shortly because the first assignment requires that. So you will need to purchase this. So this is kind of in lieu of the textbook, if you may. And I kind of scrounged around a lot to kind of see. So previous years I have used a different platform and it has its own thing. So this year I decided to use, so it's again from the same Arduino Nano family, but I'm using the one which is based around the microcontroller that Raspberry Pi people came up with, RP2040. This is called Nano RP2040 Connect. It basically has two processors, kind of these are the low-end processors in the ARM series, so M0 plus. It has Bluetooth and Wi-Fi. That's good. It has Wi-Fi, so it can directly connect to the network, but of course you need access to a network. So usually UCLA's networks, some of them require like login pages and all. They won't work with something like this. So the easiest thing to do is maybe use your phone or laptop as a hotspot and then connect to that. Okay. It has an IMU. Anyone knows what IMU is? Yeah.
Yeah.
So it has accelerometer, gyro, and I think it has a 6 DOF only, or maybe it has magnetic also. So it basically is movement related, right? It has a microphone, so that's nice. Because generating acoustic signals is very easy for us. You can do it from your phone or laptop. And then it has a temperature sensor also, which is not terribly useful there. It does support embedded AI models, so it is supported by TinyML toolchains, TensorFlow Lite, which is from Google, and Edge Impulse, which is a commercial product, but they have a free academic thing, which kind of makes it easy to train and deploy models. It runs in Arduino runtime, which under the hood, it's based around something called Embed OS, which is a pretty powerful RTOS. Unfortunately, this combination is retired, as in Embed is no longer supported by ARM. So as a result, this whole product is end of life. If you go to the Arduino page, it will say end of life. But it's available in quantities and seems to be a pretty good platform from my playing with it. Amazon seems to have many of the headless version of these things in stock. I purchased one for 21 bucks just a few days ago. There is a header full version of it, which is like 33 bucks. I think you can save a 12 bucks by buying header and soldering it yourself if you need to, and maybe you don't even need to potentially do all the headers. It does need a micro to USB-C or A, depending upon what you have in your laptop. Hopefully you have something like around, or otherwise you can get the adapter from USB-C to micro C for like $1.50 or something like that. It has an extensive set of tutorials and all. So if you just sort of go to that link that I have in this bullet, you'll see a lot of tutorials and all. So in fact, the assignments kind of build upon those tutorials. So this is my way of kind of forcing those of you come from less experience with programming and all to kind of get your hands dirty and kind of get some feel of this. Any question on this? Okay, so do acquire this because you'll need it for the first assignment. Travel conflicts, I already alluded to it. So there are two confirmed one. One is Thursday, October 9th, and the other is Thursday, November 13th. In this one, I am in the East Coast time zone. So my plan is to do the lecture but just do over Zoom. This one I'm actually in Dubai, which is kind of a horrible time, but conveniently for me, you guys will be talking. So that's the day of the midterm project midterm checkpoint presentations. There is another possible conflict, I'm not sure, on 10/21. I'll see how we handle it. There's a slight chance that I may have my postdoc talk about something out here as opposed to me doing a Zoom lecture because I'll be on a army site, and so connectivity is a little bit unsure, but quite possibly I may not go either. So those are kind of the logistics. So at this point, I think it's just about halfway point. I want to take a short break. So I want you to do this, fill out this Google form. It asks for some other information also, and it also needs a secret code. Okay. And that secret code is, I prepared it. Okay, here it is. CPS-IOT 2025. Okay. And again, let me go back to this. So yeah, just take a photo and let's take a short break. And if you have any questions meanwhile, so the sole purpose out here is I want to see who's actually here because I don't want to just go down the wait list and people are not attending.
So on Friday on the 29th position of the Willis,
What was
29th.
Mhm.
So I'm wondering if I can get the PDU just to secure.
Most likely, yes. I mean, I'm sure. I mean, you already saw two people left, so yeah, people dropping out. So yeah,
Okay.
okay, yeah. I mean, usually up to 40s or even low 50s, people get in, but just because of the attrition. Hi.
Yeah, I'm still listening to the class. Is the process for enrolling for just master student in category 3 that you left out?
Yeah.
Is it that I have to ask you for a PT or is it automatic? Will you
I'll
automatically?
just go down the wait list.
Okay.
As long as I see your name in today's agenda.
Okay.
Okay, yeah.
Thank you so much.
Sure. Hi. Oh, the code again. Here.
Also, I'm a master ECE student.
You're a master?
Yeah, master ECE student. I can say I'm on the wait list. And how likely am I?
What's your waitlist number?
I'm not sure. Yeah,
Yeah, I mean, like I said, if you're in 20s, almost certainly you'll get in. If you are in 30, I mean, I think if you're above 50, probably not.
above 50, probably not.
Yeah. Okay. Hi.
Hi, so I came late and also would like to lease we should wait till you that I can get access to the slides. I'm not enrolled.
The slides,
Yeah. Just to get time.
the Piazza page where I post the slides is public, so.
Well, I'm an undergrad, so I guess I wasn't the best for the team. And I'm not.
Yeah, send me an email, I'll just send you the link, or I'll send you the link to the Google Drive folder where I put the slides. So, okay. So,
Yes, same issue. Yeah.
okay, so just, yeah, send me. Are you a department scholar or something like that? No,
No, I'm just.
Just attend. Okay, okay.
week to for a conference, so should I just email you?
Email me, and I would need some sort of like either you send me a link to your paper that is being something that you are suggesting. Okay, yeah.
Hi, can you hear me?
Yeah, hi, go ahead.
Yeah. So, I just got admitted as well. I'm on a wait list right now. I'm number 63 actually, but I really need the class because I'm doing an MS thesis that's on the material here. Like I'm doing embedded system since my bachelor's at UCL as well. So, I already sent you an email, and I was wondering like the possibility of like getting priority of the for the PTE.
You know, if you're in 60s, it's probably very low.
Yeah.
It's very low, is what
Okay.
I say. Okay.
Okay. Gotcha. Yeah.
Yeah.
All right. Thank you.
Okay, so let's resume. So I think rest of today's lecture is kind of a whirlwind tour through what is happening in this space, what kind of things people are working on and all. This is more from a state of current research activity perspective. And then, of course, the main course is really about some of the topics, and we'll sort of go in. So it's kind of titled as Embedded Systems in the Presence of AI, like what is happening as a result. Um, okay. So one way I like to think about it is that uh, modern embedded systems are not just the little devices that we normally, or whatever standalone devices that we normally think of. Firstly, tremendous stuff happening on those devices. Just past week, you had sort of Mark Zuckerberg talk about those newer glasses and all. That's an example of a latest iteration. So a lot of action around these different form factors and all, health related things like on my little Aura ring. That's an example of an embedded system. And of course, embedded systems don't have to be tiny. They're also sort of big stuff, right? Autonomous vehicles, drones, things like that. But they don't exist in isolation. So that at least three other technologies which are kind of coming up together, right? I mean, one is just I've kind of lumped it under AI, machine learning, signal processing, control, but it's essentially the different pieces of how we perceive the world, how we reason about it, how we understand it, and how we take actions based upon that, right? I mean, these are the algorithms. Then the connectivity, and connectivity, both kind of a short hop, but also this ability to reach anywhere. I think in recent past 2-3 years, a great example has been the way warfare has gotten revolutionized with Starlink. Okay, so like Ukrainians have been using those Starlink tiny dishes, which suddenly give you like 100 megabit per second anywhere on the battlefield. And that changed kind of what military likes to call a situational awareness. And then they are able to send drones and stuff like that, right? I mean, so warfare certainly is sort of changing quite a bit as a result. And that's just one example. Okay, so connectivity, right? I mean, I think we are rapidly approaching where we can basically have good low latency, high throughput connectivity in far places. And then final bit is the cloud infrastructure. By that I mean very high-end compute resources. You can almost say like temples of intelligence, which you can access with increasingly low cost, but also you can access with increasingly low latencies. For example, in our own work, we find of that, like oftentimes people say, if you need low latency, run your AI models out on the edge device because you're local. But what we increasingly find is that for a lot of stuff, we are better off going to the cloud and getting things processed and coming back, partly because our networks have become fast, but also uh, two other things. One is that the hardware in data centers are getting optimized for machine learning a lot more rapidly than kind of the edge stuff. Okay, and the third thing is big models are able to do things much more accurately than the smaller models, and that sometimes gives you an advantage. So just to give you an example, let's say you have an autonomous vehicle with a camera, and it's supposed to detect some sort of obstacle on the road and brake. And so you might say, okay, take the image, process it, detect objects, brake. Now, the problem that you soon realize is that if a big model, but by a big model I mean a more powerful neural network, is processing the same image, it would be able to detect a target earlier, either when the target is still very small because it has better resolution capability, or maybe if the target is obscure, like a partial mosaic or something like that. Small models need to be a lot closer in order to be able to detect it. So there is that latency advantage, which also occurs because of the quality of your processing. It's not simply the computation time. So in this example, it turns out some of the work we did is that running a big model in the cloud gave us a superior time to brake than a small model running on the edge, because the additional network delay was more than swamped by earlier detection, right? We were able to detect the target from farther away. And even though the model was bigger, the compute resources on cloud are far more optimized. So these, so there's a very non-intuitive trade-offs that can occur. So what all of this is leading to is this class of systems that, like I said, cyber physical systems, cyber physical social systems, IoT systems. There's a whole soup of verbiage that exists, but just I like to think of them as these are interlinked technologies, and one should really approach them holistically. No longer do you just design stuff at the edge. It's really kind of the whole, when you're designing a system, you have to really be comfortable making design choices across these different layers. Okay, and all of this is happening in many, many application domains. I'm picking some examples that my lab works in. We do a lot of work on mobile health, where kind of what we try to do is from sensors on body or in your environment, we try to detect what are called as digital biomarkers. These are basically from sensor data, we are trying to make inferences about health that normally would require like a blood test or some other test, right? I mean, so early signs of a lot of things emerge in sensory data. And then the control action here often refers to as just-in-time adaptive intervention. It could be medicine, it could be an electric stimulation of some form, or in our case, I work a lot with behavioral scientists and all, it is some sort of an informational thing, okay? So if we detect that someone is going to relapse into taking drugs or smoking or something, we intervene in a timely manner, okay? So timeliness matters. It's not milliseconds, it's seconds, but still, it's there. Smart and sustainable built environment. Some of it is about comfort, but a lot of it is also about making things energy efficient, making things more sustainable. So our buildings are great examples of sensors, then that data being used, sensory information about the building, about the environment, about the people, and that all being used to control HVAC systems, lighting, elevators, things like that. So modern buildings are kind of a great example of these kind of systems. I already referred to battlefield things. So actually, there is a big project in the country called Internet of Battlefield Things, and I'm part of it, some other faculty also. And so we basically work on kind of, again, this kind of a perception, understanding, action thing. We don't work on offensive side, so much of what we do is more is on the defensive side. It's purely unclassified work that we do, but that's another area. Sustainable ecosystem, so a great area where sort of a lot of work. So we just a couple of years ago finished a project where we were studying animals in ocean. This was an international project, and we were putting sensors and all in order to study the movement behavior and other kind of behaviors of various kind of sea animals, for example. What the thing is, they all sound very different, but actually what my hope is to show that there is actually, nevertheless, there is a common set of challenges and design principles and all that cut across kind of embedded systems in general. One thing which drives these things quite a bit is we have sensors everywhere. Okay, I mean, just when I go back to like just earlier in my career, when I was a grad student and kind of my early job, I used to work at Bell Laboratories. there were no sensors. Okay, and then suddenly in the span of like 20+ years, I mean, we have like each one of us having gazillions of sensors. Like I said, just my little ring has multiple sensors in it, and by the time you count what I have on my watch and on my phone, things add up, and then your environment and all. Okay, and then there are not just hardware sensors, there are also software sensors. Every action, every time I touch my phone and all, that potentially the sensing action. So our phone, our spaces, our bodies, to the extent that it's fair to say that now most of the data that are produced is coming from some sort of a sensory device. I have sort of some numbers out here that kind of like you lump every other human created data. By that I mean things we write, things we speak, YouTube videos that we generate, you kind of add them up. It's swamped by what sensors produce. There are cameras which are just capturing video all over the cities and all. They're not human generated, they're just always there. Our city, like, I don't know if any of you were here during kind of the January fires. That's when I discovered that actually even in Santa Monica Hills and all, there are lots and lots of cameras and all which are there for wildfire. So those kind of IoT sensors, air quality, traffic, these kind of things are just sort of generating tons and tons of data. And once you have sensors, then you can analyze them, you can understand what's happening in the world, and then, so that's called inferences or awareness, and then you can make interventions. That's kind of some sort of a control action. So a lot of people like to think of it, this comes from kind of neuroscience jargon, perception, cognition, action happening at each node, and then you also communicate in order to collaborate. Okay, so you can think of like a robot doing it or drone doing it and whatnot. And communication is another form of action, right? I mean, my reading is not very reliable. Maybe I reach out to another agent, another embedded system to kind of combine information with them. So we kind of see that pattern, that computation is organized as sensors feed into some sort of a perception model, feed into something which does analysis, understanding, reasoning, those kind of things. Right? I mean, and then as part of it, maybe it decides to collaborate, like shared perception. I have a car going down the road and there is some truck in front of it. Maybe that car can talk to another car to then get a different view, and then make a more prudent decision. So communication, that's the IoT part, the connected part. And then action is really kind of, in some cases it's physical action, but in other cases it could just be an informational action, informing the driver, nudging a patient towards a different behavior and all. So examples of these, I already mentioned that in mobile health we kind of do a lot of it. So sensors of different types give us these biomarkers from which we try to predict the trajectory of one's health, and then based upon that we kind of make interventions of various type there. And there are major studies like what kind of impact this has on, like ultimately all of this has to improve our health. It's kind of pointless, right? I mean, so kind of there are a lot of medical studies going on to look at the efficacy of these kind of interventions. Autonomous vehicles, I mentioned, this is a pipeline. I stole it from a paper from UC Berkeley, but it kind of shows what's going on. It's organized as sensor, perception, prediction, planning, control. But ultimately, like the cars are equipped with like all these sensors like cameras, LiDARs, GPS. I mean, we see the Waymos on our campus. The perception layer kind of does perceive the environment, perceive the pedestrian, perceive other vehicles, perceive things like traffic cones and all, right? I mean, all of that has to be stitched. Then we make predictions about like what is going to happen to other vehicles, other pedestrians and all. We plan our own trajectory, and then we do the lower level control. And you'll see this pattern in a lot of other places. I mentioned smart glasses. There kind of this pipeline takes the form of sense, perceive, understand, and what's the action there? Anyone in a smart glass? Display, rendering, right? So perceive, understand, render, right? I mean, so again, that's a technology which actually we have begun to use in the health domain, because one way to intervene is I'm walking around and all, and there is suddenly some silent let's say, heart ailment kicking in, kind of a alert coming in unobtrusively through that. So there are some people exploring those kind of ideas also. So the rise of these kinds of AI-infused embedded systems, or whatever you might want to call it, there's a bunch of technologies behind it, okay? And in some senses, understanding them. So clearly, I already alluded to rich set of sensors and rich set of actuators. Sensors in particular, I think when I started my journey into embedded systems, by sensors, we meant things like temperature sensor and humidity sensor. And if you were lucky, we had an IMU. Okay, and nowadays, I mean, we have little LiDARs, like my iPhone has LiDAR, you have radars, you have kind of whole bunch of clever sensing just packed into tinier and tinier kind of volumes. And they are much higher dimensional sensors. Instead of producing a single number, they produce kind of a glob of numbers, and then you have to kind of make sense out of it. So that leads to algorithms that let you make sense out of high dimensional data. And really, at this point, kind of neural networks are basically the one, which is, I think, the big shift that has happened. And I would also say for a lot of people, it has been a bit of a root change, because most people like to believe that we understand a system when I can write down an equation for it and model it. The reality, though, is that now these systems to which we throw data, and they train some sort of the weights of these large number of neurons, and they do much better than the algorithms. So whether it's control theory or signal processing or communication theory, time and again, we are seeing that models trained from data are doing better than kind of what first principle approaches sort of brought about. Now, having said that, the first principles are still important, because sometimes these models go way wrong. So at least those first principles begin to give you an envelope, right? You can begin to think of them as shields. If they are violated, then something is drastically wrong, okay? So really, you kind of end up with these things coupled with kind of our traditional stuff. And then finally, hardware. And I've kind of called it tensor processing accelerators, but NPUs or whatever. And some of them are digital, but also we are seeing emergence of analog processing and optical processing. Like there are these passive optical neural networks. Just this week in my group meeting, we discussed a paper where using meta surfaces, which is kind of a clever type of antenna structure, they basically, what they did was, I have a embedded device, edge device, an IoT device. It's sending its sensory data, and over the air, it's kind of hitting some sort of an antenna patch, and that antenna patch essentially computes the inference, and then the edge server kind of receives that. So they call it as neural computation over the air. Okay, so people are pursuing all sort of clever stuff like that. So a lot of innovations happening out here also. Okay, so what we, if kind of, look, I'm old. I started and I was always fond of these kind of systems that interact with things. And within my professional life, I've kind of seen this transition from classical embedded systems, which is basically sensors and these first principles algorithm and actuators. So basically microcontrollers on which you are programming finite state machines and PID controllers and stuff like that, and basically doing bare metal programming. Okay, Arduinos are like that. Okay, so that's a great example. Then in 1990s and 2000s, a lot of work happened actually here at UCLA by various faculty, and that was the emergence of these networked embedded systems. I joined around that time, and that's why I called my lab Networked Embedded System Lab. But you had things like IoT and wireless sensor networks and all emerged then, and nowadays these are products. I mean, if you use Philips Hue lighting or these kind of things, these are actually networks of things within your home, as opposed to kind of centralized architecture. So a lot of innovation in networking protocols and all happen out here. Then later on, the next step in this journey was this emergence of cyber physical systems. And that was this notion that normally in computer science, for example, when you write a piece of software to prove its correctness and performance, it's basically as a piece of software. But in systems which are controlling things, which are sensing things, to say that something is working correctly or not, you have to also model the physical world. Okay, if I'm trying to control a motor or trying a robot interacting with whatever packages in a warehouse and all, you have to really reason about the cyber part and the physical part together. And that led to kind of this whole new theoretical framework called CPS systems. You can think of it as a modern instantiation of control. So if I think of this as embedded, this is embedded plus networking, then this third stage is control plus embedded plus networking. Okay, and that was a big shift happened, and I think we are kind of at the tailish end of it. And now, in recent years, and I think going forward, we are really kind of in this world of AI, various forms. Some people call it AIoT or AI embedded CPUs or embodied AI. Big shift is, instead of explicitly programming based upon control theory and signal processing theory and all, we learned from data. As a result, instead of simple modalities, which we could model, we are now able to deal with very complex modalities, right? I mean, there is really no modeling of those kind of complicated data. Instead of a hard determinism, like very predictable software, now we are in the world where at best we can make statistical guarantees, and we have to be prepared that things fail because we don't understand these systems fully. Hardware beyond CPU, I kind of already alluded to that. We are not talking about a single model. Now it's really kind of complicated pipelines of models. We saw that autonomous vehicle, there were like 4 different stages there, right? These trade-offs between accuracy, latency, energy, these kind of things, and a whole bunch of other stuff. So kind of that fall into this category. So clearly, sort of, I guess the message I want to give is that embedded systems of today and going forward are vastly different than what they were just a few years ago, let alone when kind of the field started in 80s and 90s. So we have come long, long ways. So one perspective I just wanted to offer is that how we do the processing in these systems has changed. So I call it explicit programming versus learning from data. So I just want you to walk through it. Okay, first generation of embedded system, I would basically learn how to model the signal, how to model a plant if you're a control theorist, and then basically using rules and logic and physics, we would basically write a code, run it on a CPU, and then given some runtime value X, I will produce some inference or prediction or action, whatever it might be, to do it. This kind of work for simple stuff, thermostats and microwave ovens and all, but really for, let's say, an autonomous vehicle or a robot and all, these environments are too complicated. Then we moved to the world, this is probably began to happen in late 90s and all, probabilistic models, basically based around machine learning. And if you have done an ML course, like equivalent of M146 here, so kind of the idea is we collect certain amount of training data, which is painfully labeled, and then it's used to train a model. So some sort of a small model, because these were simple models, and then we were still able to run it on a CPU, okay? And then at runtime, again, I get my test value and I kind of apply it out here. One of the key things that makes cyber physical systems and embedded systems hard is that it's very difficult to label the data. It's, if you have images or sound clips or text, you can collect, and years later, you can have someone label it, right? I mean, I can hire people on, let's say, Amazon Mechanical Turk and cheap workers, and I can have label it. But if you are trying to collect and label data like accelerometer data from your smartwatch, it's immensely harder. What do? You tell the person, keep labeling what you are doing. Oh, I'm walking. Now I'm sitting. Like, how do I label these things? So the labeling problem is pretty hard. So this approach kind of runs out of steam by the time you hit sensory data and kind of actions based upon that. Okay, oftentimes what people do is they'll put yet another sensor like a camera to capture what we call as a ground truth, and then have some poor human being kind of look through. But the volume of data is just so much, it's not there. But having said that, that did result in a lot of improvement, and you have kind of various kind of models with small number of parameters, things like support vector machines and all emerged, which kind of did this. And again, if you have done a course, you have seen it. If not, there are Python packages like scikit and all which provide you things. Linear models are simpler, but there are a lot of other things. Then came neural networks. And of course, they started in vision and language, but over the past, let's say, 10 years, almost every other form of sensory data is also being processed through neural networks. So you can just think of them as large cousins of these models, okay, large cousins of the traditional machine learning models, but much larger, lot more parameters, and therefore we also need a lot more data, okay, training data. So applying them is hard because of this data problem, data labeling problem. But kind of the first generation of these things were simple, fully connected type neural networks, which I have shown, kind of multiple layers of neurons, which are kind of loosely modeled after um, natural neurons, but it's basically a linear weighted sum together with some sort of a non-linearity. I'm sure you have seen something like this in some course or the other, but basically you can think of it as a combinational logic circuit where the logic gates are the neurons. Okay, that's one way of thinking about it. It's purely a combinational function, left to right. The input is presented out here. And so if it's an image, I can feed it the pixels. If it is some time series sensor data, I can feed the different samples of time series and then chug along through the sequence of things with each neuron is doing this. And then the output could be what type of object there is, or what is the speed, or stuff like that, depending upon the task at hand. So, and then later in the course, we'll see there is a lot more which has happened since. One of the latest thing is I mentioned earlier is this concept of foundation models. And the idea behind foundation models is that I train a model on vast amount of unlabeled data. So while labeled sensor data is very hard, unlabeled sensor data we collect all the time. I mean, every moment we live and move and do things, we are collecting unlabeled sensor data. So much like what LLMs did, right? They took lots of unlabeled language data and trained a model without labeling, and then at a subsequent stage they add on to it. Anyone knows how unlabeled training with unlabeled data is done in the world of language and vision and all? Okay, yeah.
No, like reinforcement learning.
No. Okay, so basic idea is the following. Okay. Let's imagine, so I'm going to take the text analogy, right? So no one has labeled it for anything because I don't even know the task it is, but I have text. So what I do is I mask something. Okay, so let's say I have text from Wikipedia and I have the first K words and I mask the next word. And the task I present to for training is to predict the word I have masked. Okay, so kind of the idea is in this case, instead of trying to predict a label, I'm trying to train a model which understands the structure of the data. So it could be time series, let's say it's IMU data. And so I mask some samples and the task is to predict those samples. Okay, and so I train a model. So in this case, I don't need any labeling. In case of vision, it would be have an image and I mask some part of the image, black it out, and then the task would be that. And I do it randomly with a whole bunch of stuff, right? So I'm the task I am training is that on a masked input, can it recover? And now I can use unlabeled data. And once I have this model, what is effectively doing is given sensor data or given language, it produces a representation of it, a vector of numbers, which has all the necessary information in that input. And then for my given task, let's say now I want to decide running versus sitting. I just have to train a tiny classifier on top of it. So, so my need for lots of data, lots of label data is significantly reduced in this process. Okay, so that's kind of the idea. We'll see later later in the course. Okay. So what these advanced models are letting us do is first thing is I can make complex inferences from simple sensors. So IMU is a great example. Like camera, we always suspect, we always say, okay, it's like I can sense a whole bunch of things given an image. I can sense the light level. I can sense color of things. I can sense the identity of things and all right. So cameras, we always expect. Sound, similar thing, because we relate it to a human. But what about something like IMU, which really is three sensors in one: accelerometer, so that's linear acceleration; gyroscope, which is a rotational speed, right? Again, three numbers; and magnetometer, which is the magnetic field, which is basically you can think of as giving us a direction. Okay, so magnetic relative to magnetic north. Sounds like, oh, it's about motion, but I can infer lots and lots of things with it. Okay, and that's what people have been doing. So, for example, using this, I can detect human activity. I can even detect certain physiological signals. If you think about it, when your heart beats, there's movement there. When people have Parkinson, there are tremors, right? I mean, so health conditions can be done. If you put an IMU near the throat when you speak, when you eat, right? I mean, all these complicated things that can be inferred. Yeah, okay, head movement, right? If I'm talking, my social interaction, those kind of things. You can also use it as a human interaction device. So like accelerometer in my watch, and as I tap my back of my wrist, the acceleration is being picked up, so I can use it as a virtual keyboard of sort. I can various kind of gestures, right? I mean, again, it can pick up. In fact, again, that new smart class that Meta introduced, their UI device is a band. In that case, they are not using IMU, they're using some neural signals, neuronal signals. It's kind of the same thing that I'm detecting something about gestures out here. In that project that I had mentioned, we were working with sea animals. We were really trying to detect their 3D motion trajectory because GPS doesn't work underwater, and yet we wanted to be able to track movement of animals, so we were using accelerometers there. Other type of sensors. So yeah, where again making complex inferences for where you wouldn't think that I might. So for example, let's say I want to detect vibrations remotely. Okay, so when we speak, my throat vibrates. If I'm speaking very loudly, maybe some other things nearby may, or whatever. If I have a loud sound, some other things might vibrate and all also. So one of the things always is that can I pick up vibrations remotely? Because if I can pick up vibrations remotely, then I can detect a lot of stuff. So usually, if I'm using, let's say, I want to pick up sound, then this gets confusing because there's background noise. There is sort of multiple people may be speaking, multiple things may be making sound, or there may be barriers. So one of the things which has emerged in recent years is using radio waves to pick up vibration. So the idea is if I have radio waves which can, so one example, think about it, that um, if the radio waves have very small wavelengths, then if they hit a surface which is vibrating, then that is going to modulate the return signal. And then by analyzing it, like in a radar-like manner, you can detect and recover the movement of the surface it was hitting. And then if you have radio waves which are sufficiently wideband, they can penetrate walls and all. So one cool project that a student of mine did was we were using something called ultra wideband radios, which can penetrate walls. And then on the other side, any sort of moving surface, the vibration will modulate the return signal, and then we would recover the vibrations from it. And there's this kind of work that a bunch of other teams have been doing using different kind of radio signals. Then, again, magic of machine learning. Then the other thing that these models let you do is to combine sensor data. So for example, one of the things that we did was we combined that wireless vibrometry, the ability of wireless signals to detect vibration, with camera imaging to then do real-time scene analysis. So kind of the idea is camera can tell us the type of objects there are. That at this point pretty well established technology. Given images, I can do object detection and all. And this radio wireless technology can help us direct things at selected objects. So I'm just going to give you a little demo. So what is here is, this is in my lab. We have a bunch of people with beating hearts and one bunch of mannequins which are supposed to represent dead people, or okay, and so obviously they don't have any hearts. Then this combination of sensors is able to tell us whose heart was beating and who wasn't. Kind of the idea was this is a medical triage kind of a scenario after a mass casualty type terrorist event or something. We want to be rapidly kind of decide who to pay attention to. Okay. So doing remote, I think in more recent work, we have kind of generalized these things to kind of reconstructing breathing waveforms, and also a lot of stuff where can we pick signals remotely for remote physiological signals, basically without kind of touching someone's body. We can also use these models to reduce cost of sensing. So for example, if you want to capture a 3D map, traditionally we use LiDARs. Okay, this is what you find in those Waymos, those spinning things. Okay, essentially inside them there is a curtain of laser beams and they kind of rotate. Okay, and sometimes mechanically done and sometimes it's done optically, but that's kind of the basic idea. One of the things that people have now, having said that, if I give you a single image, do you think you can recover depth from it? The depth map. Okay, close your eyes. Do you lose the sense of depth? We don't, right? I mean, we still can perceive distances and all because my brain has prior knowledge about how tall people are, the perspective, stuff like that, right? I mean, so the model information can help process sensor data. So image itself has depth information, which you can recover if you have the right model, right? If I see a big tree and a small tree and make some assumption that nature is not trying to fool me, then I can talk about it. I can combine it with radar, right? The radar gives me distance, but in a much sparser manner. And so some of the work we have done, and again, some other groups are also doing, where we are combining simple sensors to create dense depth maps so that you don't need a LiDAR. Okay, that's kind of the idea. The point, again, I guess I'm trying to make is that models can provide lots of things other than simply classification, right? I mean, it can help reduce cost. It can help provide capabilities that you otherwise might not. You also want to do these things in what is called as low SWAP, SWAP, size, weight, and power. Okay, so under embedded implementations. So embedded is in the eye of the beholder as to how much resources you have. Some people, they say, okay, I may have kind of no processing at the edge, everything is done in the cloud, in some data center. Okay, so offload to data center. Then I can have these, what I would term as kind of like, let's say, smartphone class processing. Our modern smartphones have neural processing units, they have little GPUs, processors, certainly, signal processors. And we find those kind of things in like drones and stuff like that. So I can certainly do that. So these are what I would call as higher end IoT devices. Okay, they have plenty of computing. If you are in a Tesla, you actually have a pretty hefty sort of autopilot computer. But then there is also this world of like super tiny stuff, right? Like my ring or watch, these kind of things, right? I mean, so this is the world of ultra resource constrained IoT devices. They're all IoT. Okay, it's just where things reside. So usually for some products, I mean, unfortunately, just the nature of the application will dictate things, right? I mean, I can't have a big ring in, big battery in the ring, and yet also I can't just stream information all the time from the ring to the to even my phone, let alone wide area. Likewise, smart glasses, the new current smart glasses rely on kind of your phone. If you don't rely on the phone, like let's say Quest or Vision Pro, then they are big. So nothing comes for free, and one has to kind of take into account all these multiple dimensions of things. So there's a lot of work out here. Can we do things on a chip scale stuff? How can we do stuff here on where you are willing to tolerate, let's say, fraction of a pound type things? And then, of course, what can you do if you are allowed to go to data centers and all? So lots of interesting stuff. One relevant to this third one, okay, the tiny stuff. There is this whole new sort of subfield which has emerged called tiny machine learning, and there is actually a TinyML free book which I alluded to earlier. So just download it and just try it out. I mean, in fact, some of the stuff you can even do with your smartphone, for example. So, but it's really designed for microcontroller class stuff, and it's a whole tool chain where you take train models, shrink models for a particular latency, memory, CPU target, and then you can do stuff around it. So it's pretty cool. We used these kind of methods heavily for the sea animal stuff that I was talking about, where we designed kind of a device, and you see all these little things hanging around. This is actually for doing energy harvesting, because again, another challenge is if I'm installing something on a sea animal, we can't just go and replace battery at the end of the day. So it's all scavenging energy from things, and then so there's a lot of cool stuff related to the energy side of the story there. Beyond that perception, these models also help us then understand and project or predict forward in time. So the complete, this is a picture that US Air Force uses quite a bit. It's something called, I forget the name, ENSIL models. Okay, so perception is the thing part of the sensing, but then you want to understand, right? I mean, if I see the pedestrian, let's say I see a kid playing with a ball, I have to account for that. Maybe the ball might come in the road and the kid may run, so I have to sort of give some weight to that. Projection is once I understand a scene, what objects, what are they doing, what the state is, then I can predict the future evolution and their likelihood. So there's a prediction forward in time. And then based upon that, I'm going to make my decisions, right? Should I speed or slow down or these kind of examples? And then finally, I actually have to perform that action, right? I mean, so that's the whole cycle. And to be able to do all of this, these things, particularly understanding and projection, this is currently something where neural models are not necessarily very good at. And so one other thing, which is, so I was talking earlier that sometimes you have to supplement neural models with classical models. This is one instance. So let's say, for example, I want to detect that a nurse violated hygiene requirements. They went to one patient, didn't wash hands, went to another patient, these kind of things, rule violation. Some sort of coordinated attack. Suddenly we see suspicious activities in different part of the city, and we want to stitch those observations together to raise alarm. Someone left a bag, okay, suspicious thing in some setting and but not in others, right? So let's say in an airport, if someone entered and left the thing in a place and walked away, right? I mean, these kind of things. So connecting the dot across simple events currently at least requires kind of connecting back to our world knowledge and all. So what's happening out here is, and likewise traffic rule violations and all. So neural systems are pretty good at perceiving sort of atomic events, things which are happening at a point in time and all. But this higher level of reasoning is something that simple neural models are not very good at. So there are two pathways which are happening. One is, I'm going to just jump a few slides. One is that you actually use traditional models, symbolic reasoning, logic reasoning and all. And the other one that has begun to happen is, and this is kind of coming back, that a well-trained LLM can do a lot of this kind of reasoning. So LLM, of course, deep down are neural, but they have been explicitly trained for reasoning models. I'm sure some of you may have heard of things like, well, when DeepSeek moment happened, that's an example of models which learn how to reason using reinforcement learning that you had mentioned. So basically, reinforcement learning is being used to get neural models to reason and exhibit more complicated behavior. And so people in IoT world, including a lot of work in my group, for example, we have begun to use LLMs to help out here also. So complicated world. Okay, so we have the first principle physics-based, human logic-based symbolic models, and then we have these hierarchy of neural models, simple neural models to these behemoth LLMs, which even can, I guess the latest thing I'm sure some of you may have read about, that models from both Google and OpenAI did gold medal equivalent performance at both the Math Olympiad and the Physics Olympiad. Okay, so stuff. So clearly, stuff is changing. So final bit is I mentioned earlier that we have the shift away from like training a model for a particular task to these models where a big part of the model is just trained to do any task and then we fine tune it. So this concept called foundation models emerged from a group at Stanford. And kind of the basic idea is that it's a model which is trained on a broad, large amounts of unlabeled data using that masking or some such technique is called as self-supervised learning. And then once we have that model, we can adapt it to any particular task with relative ease. That's kind of the thing. And in CPS IoT world, that is happening. So just to give you an example, let's say I want to, let's say I have some sort of data. In this case, it's vibration. This is some slide from a group at University of Illinois. So I have large amount of unlabeled data. Okay, so I previously mentioned I can mask and force it to predict, right? I mean, that's one approach of using unlabeled data. Another one is I basically ask the question. I take two instances from my data set and I basically ask the question, are they the same class? Like they do the, let's say this is vibration of cars going by on the road. Are the two samples the same type of car or different type of car? Okay, so this is called contrastive learning, self-supervised contrastive pre-training. So instead of training it on labels, I'm training it on the simple, much simpler task. Do they represent the same thing or not? Okay, and the idea is occasionally I may get it wrong, but for example, if things are collected at different places, they're probably different, stuff like that. So, and my goal is that I learn this model E, which is an encoder model, on lots of examples, such examples, so until I have a good encoder which knows how to encode the data into a representation which has learned how to distinguish things. Okay, and this is done through this loss function which compares the two. So standard neural network at that point. And then once I have done it, I take this encoder and then I train a tiny little classifier for my car classification. So I need, for this classifier, I will need some sort of training data, but a lot less amount because bulk of the model has been pre-trained using this approach. This is pretty much the technique that LLMs also use. So massive amount of data and then additional fine tuning done for alignment with our human expectations. Okay, so there's a common paradigm now which has emerged. Pre-train on unlabeled data using various kind of proxy tasks and then do some fine tuning on the task at hand. And at that point in time, you have to invest some effort in that. So these taken to its next thing, what people have begun to do is in the world of CPS IoT, if you're going to the cloud, then kind of the notion is, why do I even need to build my own models? I have LLMs and LVMs or VLM, vision language models. Can I use them? So let me ask you the following. If I gave you ChatGPT and I asked you to process some sensor data, how would you do it?
Probably prompted to tell it that this is sensor data.
Yeah, but how would you feed the sensor data to it?
Adapted as a file.
Yeah, so okay, so I can sensor data is nothing but numbers, so numbers can be anything can be represented in text with some suitable form, right? I mean, so I can represent a series of numbers. I can tell ChatGPT that I'm giving you 1,000,000 numbers and they represent the channel of accelerometer, for example, right? and then have it process it. It does pretty awful at it, but it does. Okay. In fact, some results are surprisingly good. I can also plot it and give it as an image, right? I mean, so there are various ways I can feed sensory data, and people have been exploring these things, right? I mean, feeding sensory data and asking what should the robot do now, or here is the ECG data, what's the heart rate, and actually they do. I mean, in some cases they do interestingly. Okay, so I'm going to pick up on that strand next time around. But the latest fad, if you may, although I work in it, so I shouldn't call it fad necessary, because we are trying to explore how well can LLMs and these kind of big models do on sensor processing and control tasks. And the answer is, in some cases, they do surprisingly well. Okay, where to train an equivalent machine learning model is an impossible task. And the thought I will leave you with is the following: higher level sensor processing often requires making use of our knowledge of the world. Okay. And that LLMs have in abundance. Like, for example, let's say my sensor was the Wi-Fi signals, right? In particular, the networks IMC. If my phone sees a network called UCLA_web, stands to a common sense knowledge that LLMs have will tell it that I'm probably at UCLA, right? If I see whatever Singtel in Singapore, stuff like that. Whereas training a model for all possible association of Wi-Fi SSIDs to location would be a Herculean task for us. LLMs have already undergone it because they were trained on vast amount of text. So one big advantage LLMs have is they have immense world knowledge, in addition to rudimentary for sensors, but certainly great for text sequence processing ability. So LLMs are great engines for CPS IoT, and a lot of, so hopefully we'll examine some 1 or 2 papers along this trend also. But these models running on the cloud for sure, but also there are smaller models running on your phones which can do this. So I think that's the latest stuff that is happening now, which is in this evolution of type of models. We are kind of we are into this LLMs as the compute part of IoT systems. Okay, so I'm over time, so I'm going to stop out here. Hopefully, the details today have given you enough sense whether you want to stay in the course or not. One way or the other, based upon the attendance form, make sure by 4 p.m. finish it. I'm going to assign the PTs, and after that, you are going to stay in the course in your own risk because the slot may not open up.
Oh, nice. Where at? I was, oh, so, you heard your name? No, I didn't know you said Steve. Oh, I'll be out. Yeah.
I have no answer.
Hi.